Hello students, and welcome back to the Pillow Professor. Tonight, we're going to take a slow and steady stroll through the most astonishing origin story of them all, the Big Bang. This isn't just about stars and galaxies. This is about time itself starting its tick, about everything you've ever known, seen, or dreamed of, coming from nothing. Together, we'll explore how the universe began, what came next, and what scientists are still puzzling over as they gaze into the depths of space. So, fluff your pillow, pull the blanket close, and let's unravel the universe's greatest mystery. If you enjoy this kind of peaceful pondering, please like the video and subscribe. And let me know in the comments where in the world you're listening from tonight. Let's begin with the name itself. The Big Bang. Despite how it sounds, it wasn't a bang like fireworks or a cannon. There was no explosion in space. There was space expanding. The Big Bang refers to a point in time when the universe began expanding from an incredibly hot, dense state. It wasn't expanding into anything. Space itself was stretching, pulling matter apart as it grew. This idea helps explain why galaxies are moving away from each other and why the universe looks the way it does today. The theory doesn't tell us why it happened, just that it did. It's like pressing play on a cosmic movie, starting with a blank screen and suddenly watching the story unfold. And this story starts, not with sound, but with silence and expansion. To understand how this theory emerged, scientists did something clever. They ran the universe in reverse. If the galaxies are moving apart now, what happens if we rewind the clock? They seem to come closer together. Keep rewinding, and everything, every star, planet, atom, squeezes into an unimaginably small point. That's what physicists call a singularity. It's a place where the laws of physics as we know them break down. It's not that time before this point doesn't exist, but we simply don't know how to describe it. By looking at the patterns of galaxies and how they move, scientists realized that everything once came from this compressed beginning. This backward tracing became the foundation for the Big Bang theory. And it all started with some surprisingly simple observations. Back in the 1920s, astronomer Edwin Hubble noticed something strange about galaxies. They weren't just sitting still, they were drifting away. And the farther away a galaxy was, the faster it seemed to be moving. He measured this by looking at something called redshift. Just like how a train whistle sounds lower as it moves away, light stretches out as galaxies move from us, shifting toward the red end of the spectrum. This was groundbreaking as it meant the universe wasn't static, it was expanding. And if it's expanding now, then once upon a time it must have been much smaller. This was a turning point in our understanding of the cosmos. Hubble didn't just find distant galaxies, he found a clue to the birth of everything. In the 1960s, a quiet hum was discovered coming from space. Two scientists, Penzias and Wilson, were using a radio antenna when they stumbled upon a strange static, a soft, uniform glow that came from every direction. It wasn't from Earth. It wasn't from the galaxy. It was ancient. They had unknowingly found the afterglow of the Big Bang, what we now call the cosmic microwave background. This faint light has been traveling for over 13 billion years. It's the cooled-down remnant of the universe's earliest light, frozen in time. It paints a picture of the infant universe, only a few 100,000 years old. Like a baby photo, it gives us a glimpse of what the universe looked like when it was just starting to take shape, and it confirmed what the Big Bang theory predicted all along. The universe's first second was busy, Right after the Big Bang, everything was hot, really hot. Temperatures soared to over 1 trillion degrees. Particles popped in and out of existence. Forces we know today, gravity, electromagnetism, and the nuclear forces, were all intertwined. But as the universe cooled, these forces began to separate. Quarks, the building blocks of protons and neutrons, started to form, and in a flash, time began to move forward. This wasn't a calm start. It was a storm of creation, with energy buzzing and matter assembling like a cosmic dance. But by the end of this single second, the universe had already laid the foundation for everything to come. A heartbeat into existence, and already the stage was set. In the early moments, for every particle of matter, there was one of antimatter. Antimatter is like matter's mirror twin, but with opposite charge. When matter and antimatter meet, they destroy each other in a flash of energy. So, why is there still something instead of nothing? For reasons we still don't fully understand, there was a tiny imbalance. Maybe one extra matter particle for every billion antimatter particles. That sliver of difference changed everything. As matter and antimatter annihilated each other, those rare surviving matter particles stayed behind, and from them came stars, galaxies, and eventually us. A cosmic battle of symmetry, won by an impossibly small margin, and yet that narrow victory is the reason anything exists at all. At the start, all forces were one. As the universe cooled, they began to peel apart. First gravity separated, then the strong nuclear force broke off. Later came the weak nuclear force and electromagnetism. Each force plays a unique role. Gravity shapes galaxies. The strong force binds atomic nuclei. The weak force fuels the sun, and electromagnetism runs through every light bulb and lightning bolt. This breaking of symmetry gave the universe its structure. Without it, atoms wouldn't hold together, stars couldn't form, and life couldn't emerge. These forces were like tools in a cosmic workshop, shaping reality into the familiar patterns we know today. For hundreds of thousands of years, the universe was opaque. Light couldn't travel far without crashing into a charged particle. It was like trying to see through fog. But as the universe expanded and cooled, electrons began to bind with protons to form neutral hydrogen. This changed everything. Light was finally free. Photons, tiny packets of light, could now move through space uninterrupted. The universe became transparent, and that light, released so long ago, is still traveling today. We see it as the cosmic microwave background, a snapshot frozen in time. The fog lifted, and the cosmos began to glow. It was the universe's first clear morning. Right at the very beginning, something strange happened. The universe didn't just expand, it inflated. In a fraction of a second, it stretched faster than the speed of light. This doesn't break physics, because space itself was expanding, not objects moving through it. This inflation smoothed out the universe, made it uniform, and solved puzzles that would otherwise be hard to explain. Why does the universe look so similar in every direction? Why is it so flat? Inflation helps answer those questions. It's like taking a crumpled balloon and blowing it up quickly. The wrinkles disappear, and the surface smooths out. Though we can't see inflation directly, the patterns in the cosmic microwave background suggest it really happened, and without it, the universe might have been a very different place. In the first few minutes after the Big Bang, the universe cooked. Temperatures were just right for nuclear fusion. This was the era of primordial nucleosynthesis. Protons and neutrons collided, forming the first atomic nuclei, mainly hydrogen, a bit of helium, and traces of lithium. Heavier elements like carbon or oxygen would come much later, inside stars. But these first ingredients were crucial. They filled the cosmos like flour and sugar waiting to be baked. Without this early fusion, there'd be no raw material for stars to shine or planets to form. It was a quiet alchemy that shaped the universe's destiny. After the birth of light came darkness. Not because the light vanished, but because nothing new lit up. The universe had cooled, the hydrogen gas spread out, no stars had formed yet. This was the cosmic dark ages. It lasted hundreds of millions of years, a time of silence and calm. But beneath the stillness, gravity was at work. Tiny ripples in matter were slowly pulling gas together, invisible hands preparing to light the first stars. The darkness wouldn't last. A new era was on the horizon. Eventually, gravity won. Gas collapsed into dense pockets. Temperature and pressure rose and the first stars ignited. These stars were giants, short-lived but powerful. They lit up the darkness and forged the first heavy elements. They lived fast and died in brilliant explosions. From their ashes, galaxies began to form, vast cities of stars. The universe was no longer a quiet place. It was vibrant, glowing, and dynamic. From chaos came order. From silence came song. The cosmic stage was fully set. As galaxies grew, gravity became the main sculptor. It pulled stars into clusters, spun galaxies into elegant spirals, and guided matter into filaments stretching across space. It also birthed strange beasts, black holes, places where gravity is so strong not even light can escape. Some black holes sat quietly. Others in galaxy centers became hungry giants called quasars. Gravity shaped the large-scale structure of everything, from the swirl of our Milky Way to the quiet orbit of our moon. It is the invisible artist of the cosmos. But something strange lurked in the background. Galaxies were spinning faster than they should, and there wasn't enough visible mass to hold them together. Enter dark matter. We can't see it or touch it, but we can feel its pull. It acts like scaffolding, helping galaxies form and stay intact. Without it, structures would fly apart. It makes up most of the matter in the universe, and yet we still don't know what it is. A silent partner, shaping everything we see while remaining unseen. If dark matter holds things together, dark energy pushes them apart. In the 1990s, scientists discovered something unexpected. The universe's expansion wasn't slowing down. It was speeding up. This mysterious dark energy was accelerating it. It's not like a wind or a force we can point to. It's part of space itself, stretching everything faster and faster. No one knows exactly what it is, but it dominates the cosmos, a gentle tug guiding the future of everything. While the Big Bang is the leading theory, it's not without competition. Some scientists wonder if the universe might bounce, expanding, then collapsing, then expanding again. Others explore ideas like the multiverse, where our universe is one of many. We don't know what happened at the very beginning. Was there truly nothing, or just something we can't yet see? Theories like string theory and quantum gravity try to offer answers, but for now we're still exploring. The cosmos keeps its secrets close. If the Big Bang was the beginning, what came before? This is a difficult question because time itself may have started with the Big Bang. Asking what came before might be like asking what's north of the North Pole. Still, some theories suggest a prior universe, or a timeless quantum realm. Others imagine a universe that was always there, just changing form. We don't have a clear answer. And maybe, just maybe, the question itself is part of the mystery. If you look at the universe on the largest scale, it isn't random. Galaxies form vast threads and filaments with great empty voids between them. This cosmic web stretches for billions of light years. What's surprising is that these patterns can be traced back to tiny fluctuations in the early universe. The Big Bang didn't create a uniform soup. It had tiny wrinkles, differences in density as small as 1 part in 100,000. Over time, gravity pulled more matter into those wrinkles, growing them into galaxies and clusters. These subtle echoes are frozen into the cosmic microwave background and still shape everything we see today. It's like the universe remembers its first breath and still hums the same ancient melody. Why does the universe seem so perfectly suited for life? The fundamental constants, like the strength of gravity or the charge of an electron, seem just right. Even a slight change could make stars unstable or atoms impossible. Some scientists ponder whether this is coincidence or something more. The Anthropic Principle suggests we see a life-permitting universe simply because we are here to observe it. If the conditions weren't right, we wouldn't be around to ask the question. Others suggest a multiverse, where many universes exist with different properties, and we're simply in one that works. It's not a solution, but a perspective. A quiet reminder that our presence may be rare, but not necessarily a mystery. Time feels like it flows in one direction, from past to future. But in the laws of physics, time could run backward just as easily. So why do we remember the past and not the future? The answer may lie in entropy, the measure of disorder. At the moment of the Big Bang, entropy was extremely low. Since then, it's been rising. Things move from order to chaos, like eggs breaking or ice melting. This increase in entropy gives time its direction, what scientists call the arrow of time. The reason time feels like it moves forward may be linked to the very beginning of the universe. A single moment of low entropy setting everything into motion. Before the first second, before even inflation, the universe may have been governed by quantum rules. In this strange realm, uncertainty reigns. Particles pop in and out of existence. Space itself flickers like a candle in the wind. Some theories suggest the universe emerged from a quantum fluctuation, a tiny bubble in a larger quantum foam. In quantum mechanics, nothingness isn't empty, it's unstable. Given enough time, something was bound to happen, and that something might have been everything. It's a realm where cause and effect become blurry, where the seeds of the Big Bang may have quietly waited in silence until they didn't. Looking ahead, the universe continues to expand. If dark energy keeps pushing, galaxies will drift further apart. Stars will burn out. Matter may decay. The universe could end in a cold, dark silence known as a heat death. Or it might rip apart, or collapse and bounce back. No one knows for sure. But the journey from a singular beginning to a possible quiet end is a story unlike any other, and it's still unfolding with each passing moment. And so, we've wandered through the calm yet cosmic story of the Big Bang, not an explosion but an unfolding, from the earliest flickers of time and temperature to the slow formation of stars and galaxies. to the mysteries that still drift quietly in the dark. We've followed light that has travelled for billions of years, traced patterns laid down in the first instant, and listened for echoes in the structure of space itself. The universe, it seems, is not just expanding, it's remembering. Every star, every atom, every soft breath you take tonight is part of that story, born from silence, shaped by heat, carried by time. And though questions remain, as they always will, perhaps it's enough to know that from that single silent moment came all the beauty and calm we now float through. Sleep gently, students. The universe is still unfolding,